E aí, docinho, tudo bem? Eu tô vendo não, eu só tô esperando o pessoal chegar pra ver se tá certo as coisas aí. Assina aí.
Número? Não, minúsculo?
Não, é um. Não estava aquele já por lá.
Lá em PT.
Ah,
A galera de zoando que eu nunca vi no carro.
parece um busão, né?
Parece que é bonito, né?
É.
Papo laranja.
Hã?
Papo laranja.
É.
Quando eu era pequeno, ele falava, tá parecendo um jacu. Sabe quando tem umas roupas?
Nada a ver, né?
Parecendo um jacu. Eu descobri que isso era um jacu. Eu tinha visto lá no PT, mas eu fui. Esse grupo aí tá morto, depois que o Edilson saiu.
Depois que o quê?
Depois que o Edilson saiu, não interage.
Então. Morreu.
Eu tô meio cego, hein, Edilson? Eu tô meio cego.
Volta assim.
Eu tenho.
Não usa não.
Cada dia tá mais embaçado.
Você consegue ver lá?
Não sei mais. Não é igual era antigamente. Às 13h20, né? O pessoal vai chegar às 13h10.
Ó, Marcelo, você ouviu seus e-mails? Eu estava em aula, passou o almoço, eu já vou ver para correr com a disciplina do Extra. A gente tenta passar de referendo já para poder o mais rápido possível estar tudo certinho.
Você vai ter na segunda ou terça?
Acho que sim.
Não. Vou marcar aí. Deixa eu marcar uma mesma reunião.
Que eu vi isso.
Eu adoro o arquinho 2-3. Ó, chegaram. Não estamos mais ouvindo.
Marcelo, depois você traduz pra mim.
Tá bom. Se você traduzir os
Tudo é traduzido aqui. Tudo é traduzido aqui. Carol, você sabe se o Andrei tá vindo com o Ian? Sabe se o Andrei tá vindo com o Ian?
Eu imagino, eles estavam almoçando juntos.
Acho que não, porque o que eu na sessão de regulação da
Não, sim, é bastante. Vou ver aqui o...
Não, é só pra ver se o... Porque talvez o Andrei não saiba o Ian. Tá, mas é exceção. Tudo bem. Tá. Fizeram.
Tem que usar o microfone?
Eu acho que não.
Não? Foi o Alexandre que...
Também não.
Try to open
É,
the OTP. It will not work. Maybe it's easier if you... Is this presentation?
For first one, it's shorter. It's compressed. First one is compressed.
Also copy these. Just copy here. Let's try this. Yeah. Chrome is close. Yeah, yeah. To see how to present. Presentation.
It works.
Perfect sound.
And this works.
We need the this one. Yeah, this one. Yeah, and this is the laser. Tem que fazer alguma coisa a mais?
Tem que ver só ver se a transmissão tá. Já tá. O Gabriel foi chamar o Alexandre.
Yeah, you have to use that webcam. So if you stay on the other side, it's better maybe.
O seminário quinta, então,
Vão ser 1h da tarde.
9 da tarde.
Isso, é o novo horário.
I think that's
Sorry, I
it.
can't stay.
What?
I will not cover anything.
No, the projector is above.
Yeah.
I think it's just a matter of the sound.
Ok.
Tá ok já? Tá funcionando?
É o microfone na própria webcam.
É, naquele isso, estava escrito lá.
Pode começar, cara.
Isso.
Okay, yeah.
Cara, pode começar.
Boa tarde, obrigada pela presença no ciclo de seminários da Geofísica. Desta vez vamos ter o Dr. Andrei. A apresentação vai ser em inglês. Andrei is a doctor in geophysics by the University of Frankfurt in Germany. He's working in Russia in the Institute of Petroleum Geology and Geophysics. The topic of his research is seismic tomography, seismic network deployment, volcanoes, volcanic tomography, earthquakes, structure of the crust and mantle. In this presentation, he's talking about 10 years of investigation of volcanoes in Kamchatka, Russia, with temporary seismic networks, an overview of experiments and obtained results. So, Andre, please, you can start. Thank you for accepting our invitation to participate.
Okay, in this talk I'm going to present some overview of investigation of Kamchatka, it's like subduction zones, which was performed during the last 10 years approximately. And it will be really quickly. I will not go in detail of all results. I just want to give you some impressions of what we can done, and if somebody is interested, we can discuss in more details afterwards. So, okay, and this is not only my presentation, because in all of these experiments and all of these interpretations and everything participates a lot of people. And I mentioned only some of them, but actually it should be a really long list of people who have any connection to these results, to these experiments. Okay, the group overview. So I worked, and all this work was performed in Novosibirsk, which is located there. It's Institute of Petroleum Geology and Geophysics. It has two parts of the name: petroleum geology and geophysics. Geophysics doesn't relate it to petroleum, so it's like somebody thinks that we have works in some petroleum institutes, but it's not only. Okay, and our group is focused on developing of different tomography algorithms and applying them for different structures all over the world. And since 10 years, we also finally got our own instruments and start to investigate Kamchatka, because it was most interesting. It's the only one like area in Russia where we have volcanoes or other parts. So it's, you can see it's quite narrow. To the Novosibirsk, only 4,000 kilometers away. So we use Kamchatka as natural laboratory for our algorithms and for its investigation of different active volcanoes. Okay, it's like a tectonic settings of Kamchatka. Kamchatka, it's there. It's on a very side of this Pacific fair. Circle or volcano circles, and here we have like a subduction of Pacific plates subducted beneath the North American plates and forms the Kuril Islands and the Kamchatka volcanic arcs. So, and in general, if we look on some schematic structure of any subduction zones and the volcanism which are related to these subduction zones, so it could be described in this simple sketch. So we have some subducting plate and some plate which remains there, and from the subducting plate there is some areas where the fluid is released from the plate due to some modification of minerals and releasing of the water from these water minerals. So, and this fluid which is released from the subduction plates, they rise, and sometimes it stops and forms some intermediate magmatic chambers. It could be several levels of these magmatic chambers, and these different schemes or different scales of tomographic investigations, we can investigate different scale of these subduction zones. If you're looking for original tomography, which is not the theme of my today presentations, but you can look for the form of the slabs in general structure. If you look for some smaller scales, like from 10 to 100 kilometers, you can investigate the structure of mantle wedge above the subducting plates and below the crust. And sometimes you can also would be interested in the structure of this magmatic chambers or plumbic system of exact volcanoes, and it's very shallow investigation down to several kilometers depth. So in these topics I will concentrate on these small scales and like intermediate scales investigations of volcanoes.
Excuse me.
Yeah.
Can I interrupt you?
Yeah.
I need to. Your presentation is not being transmitted online, so I need to set something on the computer. Okay?
Of course.
Aqui? Provavelmente é isso aqui. Alguém sabe usar?
Talvez start stream ali.
Mas aí você pode dizer, não?
Acho que está em bloco de notas.
Como faz start stream?
Ali tem um botãozinho bem no canto.
Demora mesmo.
Start stream.
Ah, tá. Aqui.
Ah, aperta aí. Subiu não. Cancel.
Eu não tinha no bloco de notas.
Porque antigamente a gente usava o Google Meet, né?
Ah, mas eles estão usando esse OBS.
No bloco de notas não estava aí como.
Mas não tem, o seu tempo já tá. E aí, Ale? Liga aí a transmissão do código.
Tá.
Tava no.
Tá, só que tá mostrando só a tela.
Aqui sem mexer nada.
Não. Quer dizer, eu vou ter que clicar em start screen, mas não.
Até agora não mudou nada aqui, gente.
Tá.
Antigamente eles usavam o Google Meet, né?
So they're trying to figure out how to set
Sorry.
something somewhere. Ah, eu não tô vendo isso. É?
No source.
Vai olhando. Where?
No source event.
Like this? Okay. So, e aí, Carol? Não? Tem que ser alguma coisa? Cadê o bicho? You could just display capture. Fala. Por qual? Ah, tá positivo lá. Só que ele fez uma conexão aqui. E o cabo. Entendi, então não é nem essa que tá transmitindo. É, isso daí só posso mais pro. So I think it's talvez cancele. a transmissão faz só presencial.
Será que o microfone está funcionando? Porque se o microfone estiver funcionando, eu acho que não.
A gente continuar mesmo sem
É,
transmissão.
vamos
Continuar.
Eu não vou avisar o pessoal aqui.
Porque infelizmente deu problema.
Porque só
Okay, Andre, sorry. Continue.
Okay, here it's overview of like areas where we perform our experiments during the last 10 years, and the size of these experiments, so it was really different. It could be from 10 stations, very small installations, and up to almost 100 stations installed around some group of volcanoes. So it's very different, but the same features for all these networks that we installed in the summer, then it works like independently for 1 year, and next summer we collect the data and start to analyze it and put some instruments in another locations. So it doesn't transmit any data during the working periods, and the duration of all experiments is little bit less than 1 year. So that's the common things. And this, and how do we install the stations? So usually it's Kamchatka, it's not really populated area, it's not so many roads there, and volcanoes itself, it's really difficult place to reach there. So sometimes we use some cars, sometimes we use small helicopters to put some teams and then dig. So, and in the place, so we use like different types of instruments. Yeah, it could be Fudium, that actually what we use, some Russian CME sensors, growl sensors, and also some passive sensors. It doesn't really actually matter which sensor we use. That's, so we install some concrete plate on the bottom of some holes. Yeah, this was a basaltic plate, so it was not possible to dig, but usually they dig some holes with concrete, like a basement for the stations, then install the instruments, cover it with some kind of buckets to protect from waters. And this blue boxes, it's a batteries. We do not use accumulators because we have to left it for 1 year, and usually accumulators is not possible to work for so long time. So we use one-way batteries, which is have more capacities, but it's more heavier, and sometimes we also have to remove it after the installations. Yeah, and also the problem is that for proper works of these batteries needs to have a fresh air, so it's consume oxygen to make it works. So that's why we put the tubes, and it smells a little bit. That's why it sometimes attracts some animals, and they could destroy our installations. But just manage that we have to put instruments in one hole and batteries in another hole, and if some animal or bears became, they just dig out the batteries, probably cut some wires, but it's not destroy the instruments, at least stop the records, but instruments is remain. So, okay, so we install it, then it dig, and outside remains only the GPS antenna, which synchronize time during the whole period of registrations. Okay, now I will start from some examples of installations, and first of our installations was around some Avacha group of volcanoes. This is volcano located very close to the city. It's Petropavlovsk-Kamchatsky. Well, it's the largest. It's actually 3 cities which there are in Kamchatka. They're all located almost in the same place, and all other places there are only some small villages and not the big cities. So this volcano is located only 20 kilometers away from the city, and they are active and produce some eruptions during the recent times. So it's like a eruption of this Avacha volcano in 1945. So it's explosion, small explosion, then mud flows in 1991. So this is photo taken from the city, and actually the city itself was built on some deposits of ancient eruptions and ancient deposits of volcanic effusive deposits. So it's really dangerous, but people in this city call these volcanoes like our home volcanoes. There are a lot of touristic roads through these areas, so that's was easiest ways to start investigate this station. So and in 2012 we installed 10 stations. In addition, these red triangles indicate position of our temporary station, and black one is stations of geophysical surveys. Actually, I forget to say that in Kamchatka exists a really good network of permanent stations, but these stations distributed not really uniformly, so we cannot use it for tomographic investigations because it's like usually concentrated on close to active volcano and close to some villages and cities. So it's like some spots where we have stations and all other areas doesn't cover. But for tomography we usually need very good coverage of rays and stations distributions. That's why we start to install these temporary stations. In addition, with these very good real-time stations which transmitted the data to some centers and works for more than 50 years already. Okay, so we installed these 11 stations, but that was our first installations, and due to some technical problems, most of the stations stopped to work after some months. It's not continue for the whole years. And in addition, it was some activization before we decided to install there, but just after we installed, a few days after that, all activization system just stopped on this volcano, and so we did not get any information about earthquakes. That's why we decided to repeat it after some years experiments with a little bit more instruments. But nevertheless, so it was the first experiments. We did not get any information about the sources. It was very few of them that we registered during this period. But it was enough to produce like an ambient noise tomography, which use like ambient noise and then correlate signals between different stations. And in this case, these stations could place like sources of signal for surface waves. And from that way, so we used this 3 months was enough to collect data to produce some 3D surface waves distributions. And also, what is interesting there, so in 90s, 80s, that was like a still golden time of geophysics in Russia. They have a lot of money, and they actually made a profile which crossed the summit of these Avacha volcanoes and produced some chemical explosions, so to make some deep seismic sounding profiles. And that was interpretation of this deep seismic sounding. And in this paper of Balesta, they produced very complex model based on these ray traces, travel time of ray traces. But this is just using forward modeling. They're just trying to adjust this model to fit the absorbed data. And we use the same data to produce seismic tomography profile for the same data. So this is not like for refraction waves, and using our algorithms for 2D tomography, which calls profit. And you see that these dotted lines, it's just projection of some borders from these models. And in general, the features which we can see in both sections are the same. So we have this quite steep asymmetric shape of caldera of these Avasha volcanoes. So there is one side, and if you look there on this map, you see that the caldera remains from ancient eruptions, and something like a landslide, and this is blocks which is goes down, and here we have a larger amount of some sediments, and this is like an image of this capacity of sediments and where it's collected. And the last one is just the sections which made through this 1D or 3D surface-based models. And of course it's much more smooth, but still we can see this step in this model, and of course this produces more details, but advantage of this 3D model that is really 3D, and we could see not only along the profiles, but see that there is separate like a plumbing system for both volcanoes, for Avasha and Koryakski, which is located very close to each other. After that, also for the same data, we decide not to use our, but we try to use very long time of registration, but with few of stations. We use only the permanent stations, which is only 7 of them, and trying to construct some velocities model, 3D velocity models, and actually it's confirmed our first results that we have 2 different plumbing systems for both volcanoes. And what is important that Avasha is more active at recent time. Koryakski sometimes it's produce some gas releases, but actually there is no any domes or any lava flows during recent times, so nobody sees. So it's really perfect bones without any manifestation volcanic besides the gas releases from time to time. So, but we still see some sign of magma chamber beneath, but at a greater depth. Probably sometime it will also rise, so it's like a potentially dangerous volcano, so it could produce really explosive eruption. So you can see that we use, let's say, different types of data for the same. So it could be ambient noise tomography, it could be 2D profile, active profiles, and data collected on permanent stations, but with only few stations, and it was really tested a lot with different kind of tests, which allow us to really be sure that this feature which we show here is real, so we can really resolve these features, that distribution. That's just because station is only seven of them, but the number of earthquakes was really large. Okay, after that we moved to a little bit to the north, where are located very interesting volcanic groups, which it's located here, northern part of Kamchatka, close to the end of the subduction zones. And within these groups, you see it's also in topography very clearly will be seen. It consists of almost 15 volcanoes, and all of these volcanoes have different composition, really various composition and eruption regimes. So here we have the Kuchevskoye volcano, which is largest volcano in Eurasia. It's almost 5,000 meters, like 800 meters above sea level, the summits. And it's really also good stratovolcanoes, it's basaltic volcanoes with very still eruption styles. And very close to this Kuchevskoye volcano, it's only 10 kilometers. Here, the canyon is distinct, or it's not distinct, no, it's sleeping volcanoes, so it's, yeah. Okay, and Bizimyana volcano, it's a really dangerous explosive volcano. It's only 10 kilometers away, but it's andesitic and really different types of eruptions. And the third active volcano within this group is Kalbachik volcano. It's located on the south part of these groups, which also produce like a Hawaiian type of eruptions. And all others, now it's like sleeping volcanoes, or even things that it doesn't work anymore. So, but this is really big Shkovsky volcano together with Kristovsky volcano. These two, they actually join together, and the volume of these two volcanoes is larger than summary volume of all other volcanoes in this area. So that was really big volcanoes with large amount of effusive products. So Tolbachik volcano, there was a huge eruption in 2012, 2013. Actually, that's why we are point our interest to this area. And it was really a Hawaiian type of eruptions. Open some, the initial stage it was opening of some fissures with some fountains of lavas, and then it forms very long lava rivers which covers this lava. From a summit to the end of this lava flow is approximately 20 kilometers. So it's a really long lava flows. So we installed some 1 year before the eruption stops. We were there, so not in the time of the eruptions, a little bit after that. So we installed 20 stations, and also there was some additional station from permanent one, and they worked more or less good. You see that in the beginning some of them go out of the order. It was this station just because one bear goes and pick one by another all the stations because they smell it. Okay, that's installed, and we also try to interpret. But before I go to some interpretation of results obtained of the data obtained from these networks, 1 year later, it was a really big experiment which called KISS, which is called investigation seismic structure of extraordinary volcanic system. And this is Ключевской volcanic groups, and we installed 83 temporary stations, and also in this area we have over 20 permanent stations. So in total we have more than 100 stations worked for 1 year. And here is some colors indicated that blue, light blue and green indicates the station which works more than half a year. So at least we have very good coverage for a long time. And this was really international collaborations together with Paris EPGP, Institut Physique du Globe from Paris. It also participated really Geophysical Centrum from Potsdam, Germany. They provide us with 60 instruments which were used in these installations. And also some groups from local institute in Kamchatka, Institute of Volcanology and Seismology, and this Geophysical Service. Okay, and then here I want to show you, it's like we join all this data collected on these really big networks and a small networks installed around the Tolbachik volcano. So we join all the data collected, now it's like 2 years, and also permanent stations, and produce some 3D models of like a crust and very uppermost mantle. So it's like just below the crust, what happens below the crust. And here I show it's like a VP-VS ratio, because in volcanic area it's really the main instruments to see on the features, because there is a lot of content of fluids or gases, and the VP-VS ratio is really sensitive for variation of this inclusions of some melts. So it's most prominent to and easier to see some features on figures with VP-VS ratio. So it's like the whole area. This points like this is Ключевской volcano, Tolbachik. This is Tolbachik volcano located there. And I show here 2 sections. One along these 3 active volcanoes in these groups: Tolbachik, Bezymyanny, and Ключевской. This first section. And what is interesting there, that for all these three active volcanoes, we see the different structure of the plumbing system. So they really differ, not only the eruption styles and content of the materials which they extract. Yeah, also beneath the crucial it always exists this lower crustal chamber, yeah, magma chamber, and these chambers exist and it produces hundreds of events for each day. So actually small events, and but this is active all the time. And from time to time it appears. Okay, here we can see that we have clear connection within the earthquakes and also within these some anomalies of S waves, and also it will be really clear seen in PPVS ratio. It's like a conduits, vertical conduits beneath the volcanoes, which exist almost all the times, and it works like a nipple system. So if collect some extra magma in these lower chambers, then it's reach some pressure, which allows you to open some cracks, and fluids and probably some portion of magma goes in upper parts, start to collect there, then it reach crucial pressure in this place, and then it's released like eruptions. And after the exceeded pressure released, it's all cracks closed, and it starts to collect the magmas and pressure again in a deeper part. So it's like portion of this goes from below to upper part. To the Talbachik, which produces like Hawaiian types of eruptions, you see that we didn't see any straight like a vertical columns, but it seems like there is some inclined passes probably which could change from time to time because it's not so prominent anomalies there. And also Bezimane do not connect. It seems that there is something like a very solid rigid rock in between. So these data sets which we collect really allows us to look on details of the plumbing system of various types of these volcanoes. Okay, and another, let's say this is like a regional installation, another regional installations. We are going back to the location of the city. Petropavlovsk-Kamchatsky located here, Avacha, coast of Avacha Bay, and here it's Avacha volcano, Koryaksky volcano, and also a lot of different other volcanoes. And here it's also some scientists propose that here exists some so-called Alka-Petropavlovsk structure zones, which also form Avacha graben on a coast side. So, and here we installed something like 30 stations, 32 stations actually, and 10 of them was provided. It was also made with collaboration from scientists from Taiwan Institute. They also provide some instruments, there's 10 of them. And we installed that, and then we try to collect it also for 1 year. And here I present some very recent results, because the installations was not so far away, so it was only 2019 to 2020. And here I show you the result with the PVS ratio from only 4 sections. Section 1 is this one, which goes section 2 grows the Koryak and Avacha volcanoes, and section 8 and section 9 it's like a perpendicular parallel to the subduction zones, but crossing these fracture zones. Yeah, and if you look on the section is Koryak and Avacha, you see that some amount of earthquakes occurred just beneath the volcanoes. But of course, most of the earthquakes which were registered by this network was occurred in the slabs. So, and that means that we have more or less good coverage there, and on the western part of the Kamchatka we almost doesn't have any race, and that's why we cannot really reconstruct the structure there. And here it's interesting also that we really could see these graben zones with these red lines. This is coincide with the location of Alasha grabens with a low VPVS ratio inside and like increased VPVS ratio following the borders of these grabens, the side folds of these grabens. And now I want to show you some examples of small investigations on like independent volcanoes, not going for some deeper structure. Here usually we do not look deeper than 10 kilometers depth beneath the surface. That's size, and this is a photo of Bizignani volcano. As I said before, it's located only 10 kilometers away from Luchevskoye volcano, and this is the summit of Kamin, which is already doesn't live volcano anymore. And yeah, I say that before the 13th March of, before the 1956, these volcanoes is assumed that it's sleeping volcanoes and it doesn't produce for thousands of years any manifestations, no any lava flows, no gas emission, nothing. So it was assumed, but I think in 1955 it starts the seismic activizations, which finally on 13 March of 1956 lead to really strong explosions. It was one of the strongest explosions in 20th centuries on volcanoes, but it was located in area with almost no populations, so it doesn't really lead to any harm, so no people dead within these eruptions, but the elevation of the ash cloud was, it reached I think 40 kilometers elevation, so it was really strong eruptions, and after the eruptions the summit of this volcano was completely destroyed, so it was like a oriented explosions. It's the same types of explosion like you probably heard in St. Helens in America. It's absolutely the same type, and this is like two twins, these two volcanoes. Okay, and here we install not a big search, only 10 stations in addition to 3 permanent stations, and it works quite good. And we were lucky during our installations. It was one explosion, small explosion, but it was eruption of this volcano, and actually preparation of this eruption was registered by our networks, and when we try to analyze and to use some tomography, interpreted tomography with attraction, other specialists from hydrology and from INSAR specialists also reconstruct. That's some photos of these eruptions, which is occurred 20th December, like preparations before, several days before, it was just some water steam going out, and then it become more dark ashes, some losing of ashes in the steam, and then starting 19th of December starts some reduced rock falls, and then just very short eruptions, not more than 1 hour, everything stops, so it's released the energy and again became very still. So, and during the preparations, during the 1 month of preparation, it was seismic activizations. First it starts from a deeper part. Here, like these black dots indicated the earthquakes which occurs more than 9 days before the eruptions. So all the activity was concentrated on a greater depth. But then, seismic activity moved to the top summits, and in the last 9 days, almost all seismic activity occurs close to the summit. And so the amount of the data allows us to construct some tomographic models, which is shown there, and also some people, petrologists, taking some samples from rocks there, and give some like estimation on from which depths this gases and everything is comes through. So and everything we like propose a scenario how preparation of these eruptions. So at the initial stage, the fluids accumulated in the mid-crustal reservoir at depths of about 8 to 10 kilometers below sea level. So it means the surface is 10 kilometers above sea level. So we have to add some 2 kilometers to calculate the depth from surface. So, and actually it was not so many earthquakes, and that's because here the material is ductile, so a lot of fluids there, and it's not so easy to make a cracks. So and that's why the material also propagates quite slowly, because cracks doesn't propagate too wide, yeah, and a bigger distance. So and this preparation period lasted for a longer time than the last one, the final stages. Okay, and then the pressure here reaching a critical content, temperature, fluids may start to escape from this ductile mid-crustal reservoir to the upper crust. And after that, when the fluids and they migrates, actually it's not a magma goes there, it's just gases which is released. So it's quite easy to go there. And while reaching this crucial gas pressure, it's starting to destroy something. Here we have on the top of the upper crustal chamber, we have some kind of a cork which covers everything and doesn't allow to go. Okay, it's with high temperature. It's like a I don't know how to say it, but it makes your rocks more rigid when you high temperature. It's like a small cork formed there before, and it's keep the gases inside these corks beneath. But when we reach some crucial pressure, it starts to destroy these corks, and then more and more cracks occurs, and it's like avalanche process which leads to this very fast execution and extraction of the gases, produce these explosions, and then everything starts from the beginning actually. But it's keeping still for usually for 1 year, because these volcanoes more or less produce one explosion per year. It's like an average period. Okay, and then I can show you also very shortly example of 3 volcanoes. One is Gorilla volcano, located 70 kilometers to the south from the Petropavlovsk-Kamchatsky. Udina volcano is part of the Ключевской volcanic groups, and Kambalny volcano is located as the southmost volcano on Kamchatka, and all of them trying to investigate using some installation, and I will show you some models of these volcanoes. Okay, that was installation around the Gorilla volcano. It's a shield volcano. It's relatively flat, so it's elevation from a bottom of the edifices to the summit. It's less than 1 kilometer, so it's quite gentle volcanoes. But you can see it's a sign of really good caldera, which was formed like a series of really strong explosions from 300,000 years to 30,000 years before that. In this period, that forms a series of explosions, this caldera, and new volcano, basaltic volcano, rose in between this caldera. And what we found, when we start to trying to find the optimal 1D velocity models, looking at and trying to find optimal one by grid search, we just trying different starting velocity model, different gradients in the upper crust, and say what will lead to the less to the smaller amount of residuals when we calculate travel times in model and compare it with observed travel times. And just by mistakes, we put very low VPVS ratio, and then everything fit. So it's really low VPVS ratio almost in all area. So it's like we have high VPVS ratio in the top, where you have like a basalt cork, which covers basalt layers, and then beneath these basalt layers, which also plays like a cap, which doesn't allow to gases release through these very rigid basalts. And 2013, 2014, this volcano was in like activizations and it produced a lot of gases, which goes out only through one fumaroles, which produce about 11 tons gases per day. So, and these blue regions, so regions with very low VPVS ratio, and also we found these upper crustal magma chambers. And if you look at this top of these anomalies, it's more or less a little bit more smooth, but it's the same like a surface. So it's just 2 kilometers below the surface. And this features at the top of this high VPVS ratio, that's like a limit where the gases, where the water start to release from the, where the pressure became less, and it allows to gases which was inside the fluids, like in magma, was saturated in magma, it start to release from this magma. And it's always occur at 2 kilometers depth from surface. It's in many models which we produce for different, and not only in our studies. It's like these features observed at many volcanoes. So, and why it's so low VPVS ratio? So we also look in some literature and find that it could be a sign that this rocks is saturated with really dry gases. So it's filled like a sponge, and it's decreased VP velocities because we have a lot of gases, and for pressure wave, it's like became harder to propagate through these gases porosity, but the matrix still works, and for compression waves, for shear waves, they are almost doesn't change the S waves in this medium. So it's, and altogether it leads to a really low VPVS ratio. And also it was like activization, but almost all the earthquakes. So for tomography we picked something like 150 events which were located, tectonic events, almost all around this area. But actually we detect thousands of events which occurs directly beneath the summit in these conduits. And we perform cluster analysis, like using back projections and some matching algorithms. And it allows to separate 5 families of earthquakes with the same form of the signals. So if you use some correlations of the signals, they are keeps the same for thousands of events. So it's like repeated events, so like long periods events. And these families, they are consequently change each other. So it's one times it works one families, then it's gradiently shift to another families, and then little bit change the shapes, and we have some difference. So we interpreted like within these conduits, these gases continuously released, and it works something like a whistle. You can imagine that it's produced some kind of sounds, and these sounds actually, the form of these signals, it depends on the form of this whistle, of this conduit, of this tube where the gases goes. But this time the shape of this tube could be changed. It could be due to some increased temperature which melts down or closes this, and start to open a little bit narrower next to them the fractures. So the shape of this conduit will be changed, and this leads to change of the shape of the signals. So it's like evolution of this bounded systems. And then using this like the 5 templates, we also are using matching algorithms. We found like several dozens of thousands of these repeated events, which could not be picked and could not be seen by eyes, but if you're applying some correlation algorithms, be extracted from this data sets. Yeah, another example, it's really small, it's Kidinal volcanoes, it's close to the Telbachis volcano, and also was assumed that it extinct volcano, but suddenly it started to produce some seismic activizations. And in this area, there is no any permanent stations. The permanent station located a little bit side of this volcano, so it was not possible to exactly locate these events, and that's why we decided to install some small networks, only 4 stations around this volcano, and that allow us to register and locate some events. And again, we try to make a tomography inversion for this data, despite that we have only 4 stations, and usually scientists they claim that it's not possible to use only 4 stations to produce reliable results, tomographic results. But yeah, we get something. Of course, it's really rough, and what I want to mention there, that also for these magma chambers, they usually have really high VPBS ratio, and for volcanic area, it's because we have increased P velocity, just because usually in conduits you have material which goes from the deeper parts, so it's usually more dense than outside area, so it leads to increased VP velocities. But also this volcanic area, and it's saturated with some fluids, which leads to decrease of S velocities. So, and it's a really common features for volcanic areas that P velocity model and S velocity models, they behave in opposite directions. So it's increase of P velocities and decrease of S velocities. So usually if you have some amount of fluids, you have to expect that the velocities of pressure and shear waves would behave in different ways. And I also here like example some preliminary results we just got 1 week ago Brazil for Bebeduras 1 activity. We try to apply this tomography algorithms, and we also find for this signs of opposites anomalies for VP and for VS for these swarms. So that's probably indications that a lot of water in this case inside these rocks, which is also saturated. So but they are inverted absolutely independently, and they just opposite to each other. Yeah, and then Kambani volcano, it's the southmost volcano, and also produced unexpected. It was for a long time sleeping volcano. Again, it's produced some eruption in 2017, and 1 year after that we installed 10 stations around this volcano. And what is interesting is there that this is a volcano, and on the flank of this volcano there are some hot springs, and also here it's power located station, and also here located geothermal stations, small geothermal stations, but they could extract. And when we analyze our data and perform some seismic tomography, what we found that it seems that feeding system for Kambani volcano and for these hot springs actually separated from each other. Probably that's not the same, and it's the sources of these hot springs go somewhere from northern part. And again, we see this like mid-crustal chambers and upper crustal chambers, and a lot of meteoric water goes from above. And this final volcano, which our most recent installations, it's Ebeka volcanoes. It's located on Kuril Island already, so it's the Kamchatka end, and down to the south it starts the Kuril Island Park, and this is northernmost island in this arc. And Ebeka volcano, it's active since 2017 and still ongoing activity. It produces like this clouds of ashes which go up to maybe 4 kilometers, but usually only up to 3 kilometers, maybe 10 times per day. So it's phreatic, small phreatic explosions. And yeah, I'm close to the end. And we install 20 stations. It's really harsh conditions because we have only a small town there, and all other parts is really wild. It's only rich, no roads at all. So we use some helicopters to put some stations, helicopters, boats, and quadrocopters. No, not quadrocopters, quadricycle. But also, when we try, the picking for this data is still ongoing, so we do not really produce the seismic tomography model. But we already could produce some ambient noise tomography models, because you can use these rough waveforms. And for some stations, we apply when we calculate some daily cross-correlation functions. It's shown in these figures. You see that it's inclined. That means that blocks on our stations lost the connection with GPS, and all the blocks was wrong, so it was a clock drift. And using these cross correlations, we were able to extract this clock drift. You see that everything is okay, and then it lost the connection with GPS and start to drift. So then we just correct for this time shift and use it for produce some preliminary surface waves tomography for S waves, surface waves extracted from ambient noise and from correlation of ambient noise. And what is interesting here is located the summit of this volcano. It's a Vernadsky Ridge. It's like along the subduction zones. It's a volcanic ridge. And also on this part we have some hot springs, and in this part we have some deep well which was revealed in 1995, something like that. And it also was some attempt to reach some hot waters to make some maybe geothermal plant put there, but it was unsuccessful. They drill more than 2 kilometers or something around 2 kilometers. It doesn't reach any waters, no hot, nothing. So it was dry well. And what is interesting here, if you look on the location of these wells, it goes through this increased VS velocities, and usually increased VS velocities. So if you have more fluids, it leads to decreasing of velocity. If you have less fluids, it leads to like increased S velocity or normal S velocities. So if you look at relatively high velocities, and you see that they are just drilled in really wrong places. They do not perform good recognition works and did not put it in the correct place. So hope that after we will invert the body wave race, it will allow us to go deeper, because there we can go only down to maybe 4 kilometers, because the distances between stations is not too much. So, but still, we already have some interesting features there. Okay, that's almost all what I want to say. And these experiments in Kamchatka allow us, the group, to develop tools and also to test it and check it that everything is goes and apply. And we publish, I think, dozens of publications on the basis of this data. And we also already really good in installation, and we know how to work in these conditions, how to install stations in these conditions. And now the Kamchatka became one of the most studied subduction volcanic systems actually. And we're really free to share this data. If somebody interested to test some different type of algorithms or anything, we can provide this data if you contact. So it's not a problem if somebody interested to check our results, or probably they have some idea how we could use it. So yeah, that's on the way to this Rebecca volcano, which is not very high, but the hiking there is not so easy. Yeah, and sometimes it produces ash clouds which goes on your roads, and you have to wear some things to keep breathing. Yeah, thank you.
Thank you.
Thank you for your presentation. We may now open for questions.
Yeah.
From your side. Anyone?
Yeah.
Yes, Professor Andre, I have a question, and first of all, this may be trivial, but I'm an
No, it's okay, yeah.
undergraduate. So when you refer to ambient noise in the data you're analyzing, you're referring to natural seismic activity or some background
Yeah,
noise?
I can explain a little bit how it works. So we have station installations, and for this technique of ambient noise, we do not really need to register any earthquakes or any blasts, because we always have some natural sources of seismic energy. It could be tidal waves, it could be some winds, but the most of the energy is produced from tidal waves, and it's distributed all over the signals. And if you register these signals for a long period of time on different stations which located close to each other, and then if you correlate these signals from one station to signal from another station, with some shift it will correlate. So if you produce some correlations, it will somehow, it's a kind of green function you produce, which is make you like simulate that now the stations place like sources of seismic signals. So one station is sources, and all others it's like registers. So we have a surface waves which propagate from one station to another. So you just extract it, and in this case, earthquakes and blasts will place like a noise for your signals, because you have to cut out the signals from real earthquakes from this ambient noise, from this where with eyes you didn't see nothing in this data, but you can extract actually. It's by correlation. So yeah, it's natural source.
When you use ambient noise, do you use jointly with the earthquake data? Or just one single?
No, that's independently, but yeah, we want to able to develop the algorithms which could invert together this ambient noise, the surface waves and the body waves. So because in our algorithms for surface waves, we really invert in 3D. So change the dispersion curves, how it will change the dispersion. Because usually people produce a number of 1D velocity models and then just like interpolate it to 3D media. But this is, in this case, it's really 3D inversion for surface waves. And
these results that you show is already using this code of 3D inversion of surface waves.
Yeah, but also we want to
add
the possibility to invert together surface waves and body waves.
When you have many years of operation, do you see that if the velocities change during
Yeah. The
And
performance.
can you use that to predict any eruption?
Predictions, it works, as I say, with busy memory, because it works. The problem with seismic tomography is that, especially in installation, in our case, because we don't have real-time transmission of the data, so we have to collect the data and then to analyze it, and for predictions it takes several years to get the results from the installation of stations, so it doesn't work. But for time variations within the volcanoes, I didn't show it here, but we perform the time-dependent tomography inversion for Plutchevskoye volcanoes, because just about the volcanoes installed a lot of these permanent stations, and it's continuously produce this deep seismicity in this lower crustal chamber, magma chamber. And it's really changed within the time. Just within several years, the structure of these main conduits really changed. This deeper, like a lower crustal chambers, it skips all the times. It's really high BPVS ratio, a lot of earthquakes. And then, like I show there, it's from time to time appears chambers in the middle crust, and then just before the eruptions, it appears very shallow chambers. Then occurs some eruption of Plutchevskoye volcanoes. Both upper and intermediate chambers disappeared, and only the one remains. And we also, why we are trying to do this, because first of all, we collect all this data for 20 years and trying to make inversion the whole data sets. It was real-time residuals after inversion just few percents, and we cannot explain the velocities. And then we just separate by times, and it leads up to 30 or sometimes to 40% for each period of time. So the structures can explain much more residuals for different times, because it's really change with the time and very quickly change with the time in these volcanic areas. Yeah.
Thank you for the presentation, Andre. And in one of the first slides, you showed a map with the locations of the volcanoes and the magma content.
Yeah.
From basalt to andesitic magma. And my question is it possible to find a relationship between the DPVS ratio pattern and the magma content?
Yeah.
Volcano?
First, I'll show you this volcanoes. And if you look on these pictures on there, there's andesite, and here it's basalt, something like we have some here, it's like some fault, and from western part we have mostly basaltic eruption types, and in eastern part mostly andesitic. And if you look for tomography model for this area, you see like most of the andesitics volcanoes located in these areas with increased S velocities, so it's like also this high BPVS ratio. So it's with a hot mantle below the crust and this cold mantle below the crust. So basaltic volcano located above the cold mantle, so it's somehow, because it's cold, it's more brittle, and if pressure below the crust reaches the crucial contents, crucial values, it forms the cracks which leads close to the surface, and the basaltic magma from a bottom just directly reach to the tops and release there. But for the hot materials, like it's ductile, and its forms propagate more slowly and contaminate with the crustal material. So, and probably that's why it's produce andesitic eruptions in this part. But yes, yeah, we see that there's some kind of this fault, which is also proposed by geologists without any information about tomography studies. It was proposed before our investigations, the location of these faults, and the anomalies just follow this.
Does any of your tomography codes also invert for attenuation or just velocity?
Yeah, we also have codes for attenuations. I didn't work with these codes, but in our group we have these codes, and for some of attenuations, yeah, we try to produce it, I think, for Gorilla volcano, and also not in Kamchatka volcanoes. We produce some models for Arabian, some of the basaltic fields, and some areas. Yeah. But it's possible, yeah, to use some T-stars, I think, and we work with close collaboration from German Luca Di Siena from Mainz Institute, and he's more familiar with this, yeah, attenuation stuff. Yeah.
All right.
Consultate, yeah, like consult us, yeah, from time to time.
Any other questions? Thank you, Andre.
Okay, yeah, thank you for listening.
Marcelo, depois a gente precisava conversar do dado de bebedouro.
Não,
Umas coisas estranhas lá. Hã? A produção de dados de sismos.
Yeah.
Nós precisávamos conversar melhor disso. Porque o MIPO não leva em consideração a altitude. Mas ele é posicional o evento no lugar certo. Dentro da estrutura sedimentar. Por exemplo, os resultados de André, todos os eventos eles não são daquele jeito. Não estão tão rasos que nem os do Gabriel. Estão indo até 1 quilômetro. The earthquakes in Bebedouro goes until 1 kilometer. Something like that. 1 kilometer down. And they have a tendency from the south to the north. So they go deep together with the water content. And most of the earthquakes are on high VPBS areas that are really related to opposite anomalies of P and S velocities. So, yeah. So on the tomography, the result shows that all the earthquakes are laying over oppositive anomalies. Like the VP goes, I don't remember, high VP and low VS than the average model. What is quite interesting. Exactly.
Not all of them, but most.
Yeah, and it also delineates the patch from the two clusters.
Make it simple to slide, contain more water.
There is a corridor of low VPSs connecting both